This series is literally for everyone. Whether you're just curious about how robots learn, or you're a PhD mathematician working on cutting-edge AI, you're in the right place. If you're more advanced, we'll be ramping up very quickly in the next few episodes. But for now, let's start at the beginning. One branch of artificial intelligence is called robotic machine learning. Think of the machine as the robot and the learning as the skills it needs to perform tasks. This is part of embodied AI, AI that doesn't just live in computers, but interacts with the physical world. And today, some of the most exciting advances in embodied AI are what we call vision language action models, or VLAs. These models connect three things: what the robot sees, what it understands or is told, and what it actually does. It's this combination that's allowing robots to go beyond rigid programming and start learning more naturally the way people do. Now, here's the key. The fuel that powers all of this is data. Take ChatGPT, for example. It learned from oceans of data, text, code, images, and more scraped from the internet. With over 200 zettabytes of content online, it's like giving a student every book, movie, and newspaper ever made. No wonder it can answer so many questions. But for robots, the situation is very different. Robots don't have Instagram feeds labeled with robot joint angles or YouTube videos tagged with motor commands. The kind of data they need, robot actions paired with real-world results. This doesn't exist in bulk online. That's why VLAs are so tricky. They don't just need words or pictures, they need synchronized streams of vision, movement, and outcomes. And they need it in huge amounts. It's expensive, it's time-consuming, but it's also the reason we're on the verge of robots that can learn new tasks without teams of engineers programming every little step. If you open almost any recent research paper, you'll see the same line repeated: we trained our model on a high-quality data set. But what does that actually mean, and why does it matter so much? Imagine teaching someone to drive if they only ever practice on a sunny day on the same road with no traffic. They'll probably fail the moment it rains or when they hit a busy intersection. Robots are the same. If your training data only shows them one version of success, they'll stumble when the real world throws a curveball. Your robot will perform best when the evaluation setup matches the distribution of your training data. That means show it successes in different ways. Avoid feeding it lots of failed attempts. Cover variety, but keep it consistent. Say you record 50 demos of a robot picking up a red cube in the center of a table. It'll nail that task, but place the cube off its mark or swap it out for a different object, and the model fails. Why? Because that new situation is out of distribution. It's like asking a daylight-only driver to suddenly handle a midnight snowstorm. In this series, we'll show you the principles, insights, and best practices for collecting the kind of data that lets robots adapt, whether it's picking up objects, following instructions, or responding to verbal cues. So stick with us. By the end of this journey, you'll understand not just what machine learning and robotics is, but how to do it right.
Trossen Robotics, helping innovators innovate.